Hello, my name is Sean Kondas. Welcome to my presentation. I'll be talking about induced seismicity as a result of quarrying in Plainfield, Connecticut in 2015. This is some of my thesis research at Boston College. And basically what you're looking at is a picture of a quarry in West Roxbury, Massachusetts. Now I picked this picture because it's pretty cool looking and also because it gives you a good sense of just how much mass can be removed from the crust of the earth in these operations. It makes you think, surely, that these operations cause big changes in the stresses of the earth. The question is, are they enough to generate or induce earthquakes? So January 12th, 2015, magnitude 3.1 earthquake occurs near a quarry in Plainfield, Connecticut. This figure shows the main shock, the portable array installed shortly after the main shock, aftershock locations with depths, as well as faults that are mapped in the area. These two brown dashed lines represent the west dipping Lake Char fault, and there's another fault that is seen in the northwest corner here, which trends southeast, and it's inferred to be strike slip, about 90-degree dip. Now, these aftershocks are numbered in chronological order. Pay attention to how basically over time the alignment and the distribution of the aftershocks changes. So at first, these first 8 aftershocks are in line with the west dipping Lake Char fault, and then slowly they change to aligning with the southeast trending strike slip fault. And then they change again to being sort of evenly split between the two distributions. So my objective here is to evaluate the possibility of whether or not the quarry activities induce these earthquakes. So crustal unloading in a contractional setting can lead to rock failure, at least from a rock mechanics point of view. So if you look at a more diagram in a Coulomb fracture criterion, you can see that increasing differential stress in rock can cause it to fracture. And specifically, in a contractional setting, your maximum principal stress, sigma 1, is going to be horizontal. Your minimum principal stress is going to be sigma 3. And if you are unloading in a contractional setting, you're reducing sigma 3, being the vertical stress, and increasing the radius of the circle, bringing it closer to this line, which represents failure, and is given by the Coulomb fracture criterion equation. Important thing to note is that this diagram applies to failure in unfractured rock. So when you have slip on fractured rock, for example, slip on a fault, or the west dipping Lake Char fault, to be very specific, the failure criterion is actually shifted down a little bit. So it's easier to reach that failure. And so here's the focal mechanism computed from the main shock of the Plainfield 2015 earthquake. You have a thrusting mechanism, which is expected for a contractional setting, and the thrust occurs on a plane that is trending roughly north-northeast. So there's strong evidence to suggest that crustal unloading caused the Plainfield earthquake in 2015. So the next thing we want to do is model the stress changes in Plainfield to see if we can bring stronger evidence and insight to the process. But first, to do that, you need to determine the subsurface structure in the area, for example, with fault orientations. And so we do that by first conducting a gravity survey in the summer of 2019, so this is last year. We did a gravity survey shown by this figure here. You can see the gravity survey area around the quarry in red, the aftershocks yellow, the main shock is the blue star, and this is on a DEM over a hillshade map, so you can kind of see the elevation distribution in the area. And also these black lines are the mapped faults. We took 113 gravity measurements at each of these green triangles, and they're spaced about 600 meters apart, and they were taken on public roads in the area. So here is the resulting simple Bouguer anomaly. that we computed after finishing the gravity survey itself. And as you can see, there's a maximum gravity anomaly in the southwest here, which corresponds to higher density material. And there's a minimum in the northeast here, which is about 8 milligauss versus the maximum of 20. And this is it supports the notion that there's the west dipping Lake Char Fault, pretty shallow dip, because you can see there is a gradual increase in the gravity readings as you go further west. Additionally, we decided to extend the length of the strike slip fault based on this gravity data and aeromagnetic data. So we used that information to input into our model, which we use a program called 3D deformation to essentially determine the change in Coulomb failure stress on the Lake Char Fault as a result of unloading at Wauregan Quarry, which is the quarry in Plainfield. So here we have the output of that, or basically the results of that model. And this line, this black line here, is the west dipping Lake Char Fault. This line is the strike slip fault. The yellow dots are aftershocks. Again, the main shock is the blue star. And basically we impose a east-west oriented maximum horizontal principal stress of 14 megapascals. And we have a calculated unload of 0.57 megapascals over the quarry area, denoted by this white hexagon. So now if we zoom in on the quarry area, you can see there's about a 400-meter wide ring around the quarry perimeter, corresponding to increased change in Coulomb failure stress. And this increased ring of change in the stresses, the Coulomb failure stress, aligns with many of the aftershocks, as you can see. And there's a darker sort of lobe on this side, and then there's also kind of a mirror image of that dark lobe on the other side, which suggests that the area around the quarry was actually kind of popped up. And so there was, following the main shock of thrust on the Lake Char Fault, there is potentially a back thrusting, which we investigate further with this cross section from A to B. So here's the cross section. You can see once again, the yellow dots are the accurately located aftershocks. The main shock is the blue star. And the main things you want to pay attention to here are, again, the spatial and temporal development of those aftershocks. So again, we have the first 8 aftershocks, and they all kind of align parallel to the dipping Lake Char Fault surface. And you can see many of the first aftershock events kind of occur close to the interface between the negative being the green and the positive being the yellow surfaces of Coulomb failure stress. And look, again, the second phase of aftershocks that was kind of looking like it lined up with the southeast trending strike slip fault, kind of the distribution starts spreading out a little less predictably. And then again, the latest aftershocks that were measured are kind of even more dispersed. So that brings us to the conclusions. Basically, the 2015 Plainfield earthquake swarm was very likely a result of mass unloading due to rock excavation at Wauregan Quarry. Quarrying operations can trigger seismic activity in settings with contractional stress regimes and critically angled faults. And located aftershocks and Coulomb stress model suggests slip first developed on the Lake Char Fault, followed by a back thrust rupture. Plainfield upper crust already is kind of assumed to be near critical stressed, and there have been many measurements to support that notion. And basically, small increases in Coulomb stress changes are enough to cause failure, which is what we see through the modeling. Anyway, thank you. And I'll take questions.